see about the subject electromagnetic field theory. It's a third semester subject for BE and also for ECE and various electrical faculty branches. So in this there are 5 units. In the 5 units, first unit is about the basic concepts on the vector. So why we are seeing vectors in electromagnetic fields? Electromagnetic field, the various quantities involving in electromagnetic fields are vector quantities. The force between the two charges, force per unit charge, the potential, flux densities. So they are vector quantities. So in this regard, we are going to see some vector fundamentals, mathematical vector fundamentals. In this manner, we are seeing the first unit about the vector quantities. So basically 3 types of vector quantities: the coordinate system, rectangular, cylindrical and spherical coordinate systems, and what are all the various relationship between any two coordinate systems. Using this we can convert the one into the other. The definitions for gradient, divergence, curl, and the relationship between surface integral and the line integral, and also volume integral. So in this we are saying Stokes theorem and divergence theorems. The second unit about electrostatics. So electrostatic is, so it is dealing the field about the electric field. Electric field produced by any charge, the point charge, the rest charge. So in this, so what is the force between any two charge? It is being derived by the Coulomb's law. And the force per unit charge, that is nothing but electric field intensity. The potential, so potential at any point of the electric field, potential difference, electric flux densities. It's all about electric field. The third unit is about magnetostatics. So magnetostatics deals with the field, magnetic field. So magnetic field produced by the moving charge. Electrostatics dealing the field due to a rest charge, static charge, but magnetostatics deals with the magnetic field produced by the moving charge. It is nothing but current. So here we have the theories about the magnetic field, Biot-Savart law, like Coulomb's law in electrostatics. Here we have Biot-Savart law. Magnetic field intensity due to a finite and infinite wire carrying a current I. Ampere circuital law. So like Gauss law in electrostatics, here we have Ampere circuital law. Lorentz law. So Lorentz law is saying about the combination of the two forces, electrostatic as well as the magnetostatic forces, and also the mechanical movement taking place in the conductor. So in this regard, we have torque and moment in the conductor. So these are all the chapters in magnetostatics we are going to study. The fourth unit is about electric and magnetic fields in materials. In previous chapters, we have seen the magnetic and electric fields only due to the spatial point charges and moving charges. Here, the same electric and magnetic fields, but in materials. So here we are considering capacitor as an electrostatic material and inductor as a magnetic material. So how we can relate the field mathematically, how to calculate magnetic field in inductors and electrostatic field in capacitors. So in this unit we are saying about, and also the boundary conditions for electrofields and magnetic fields. So it's all about the topics involving electric and magnetic fields in materials. Fifth unit is electrodynamic fields and electromagnetic waves, electrodynamic fields. So even though it is being considered as a static field, in general the field is purely dynamic field. whether it is a electric field or magnetic field, it is a dynamic field. So in this manner, so we are considering this field as a time dependent quantities. So with respect to time, they are changing. So in this manner, we are analyzing the electrodynamic fields, electric field as a dynamic one, and also the propagation of the waves, electromagnetic wave, because the wave is due to electric as well as magnetic fields, and the properties of that electromagnetic waves, the various physical parameters involved in determining the electromagnetic wave parameters. So these are all we are going to see in unit 5, and also the pointing theorem. So pointing theorem deals with the electromagnetic wave energy. So when they are propagating, the energy produced in the propagation of electromagnetic waves. So theoretically and mathematically, how to evaluate the electromagnetic waves. So these are all about unit 5, electrodynamic fields and electromagnetic waves. Let us start with the unit 1. So electrostatics is the branch of electromagnetics dealing with the effects of electric charges at rest. So here we are electrostatics. It's a study about electric field due to the point charge which is at rest. So we are considering the charge is at rest. But in general, so everything is changing with respect to time. But considering this as a rest, we are studying. We are using this electrostatic chapter, the field of charge which is at rest, and the fundamental law of electrostatics is Coulomb's law. So here Coulomb's law is determining the basic for electrostatics. So electromagnetic is everywhere. So in the universe, so considering so many materials, living and non-living, so everything is being made up of the charges. So we are saying electromagnetic is everywhere. It's a fundamental to advancement of electrical and computer engineering technology, and also it is dealing with the principles of electromagnetic phenomena in terms of relatively simple laws like Coulomb's law, Biot-Savart law. The applications. So in the applications, electromagnetic field is generally applied in almost every communication field. It's the emerging field now, even though it is an artificial intelligence field. The communication is the fundamental for this technology up to artificial intelligence, and the few more technologies which are going to be upcoming. In all other fields, the electromagnetic field is the fundamental for any communication. The communication is due to the electromagnetic fields. So wave propagation, that is due to electromagnetic field. So wireless communication, it is possible only because of electromagnetic field. So in this manner, we have so many technological advancements. Still now it is coming up. And various communications related to computer applications also, we have electromagnetic applications. So the energy produced due to the solar, wind, the emerging technologies. So these generation as well as propagation is possible because of electromagnetic applications. In defense applications, and also biomedical applications involving living things, biomedical applications. So it is due to the electromagnetic waves, using electromagnetic waves, and so many outputs, the results given by the machine, so are analyzed by the electromagnetic parameters only. So it is three-dimensional vectors. It is dealing about the three-dimensional electromagnetic field. This is a three-dimensional. So that's why we have some difficulties in attending the problems involved in the electromagnetics. So in general, electromagnetics is a study of charges at rest, in motion, and also in rest. So electrostatics charges, here the charges are being considered as at rest, no time variation. So with respect to time, there is no change in the state of charges. But magnetostatics, here we are dealing about the charges, changing charges due to time. With respect to time, there is a change in the every state of the charge. Electrodynamics charges are in time varying. So it gives rise to waves that propagate and carry energy and information. So here electrodynamics, it is also a time varying. So difference between magnetostatics and electrodynamics is, so where in magnetostatics, here we have variation, but with respect to time there is no variation. It is steady motion, steady changes in magnetostatics. But in electrodynamics, it's a varying changes. So not a constant one. In this way, we have differences in magnetostatics and electrodynamics. So what is charge? A fundamental conserved property of some subatomic particles like electron, proton and neutron. So we have atom is a finitesimal particle. In the atom too, we have three types of subatomic particles: electron, proton and neutron. So they are considered as charges. Electron negatively charged, proton positively charged, and a neutron chargeless or neutral. The charge for electron is 1.602 into 10 power minus 19 coulombs. That means, so for constituting 1 coulomb of charge, we need 6.24 into 10 power 18 electrons, which is constituting for 1 coulomb of charge. So charge is assumed to be continuous on the macroscopic level. It is being considered as continuous. It is conserved. The energy in charge is being considered as a conserved one. Scalar and vector fields. So scalar is a function that gives as a single value of some variable for every point in space. So without mentioning time, here we are mentioning every property of a function. For example, so voltage in volt, current in ampere, energy in joules, temperature in degrees Celsius. But vector quantity, so not only giving the magnitude but also the direction. So in addition, we have mentioning the direction. So that quantities are classified as vector quantities. For example, velocity. So speed is a scalar quantity, but velocity is a vector quantity. Momentum. So here also we are mentioning the quantity in magnitude as well as its direction. Acceleration is also mentioned by the direction, and force. So these are all examples for vector quantities. So examples for scalar fields. Temperature is a scalar quantity. Here we are mentioning the temperature, degree Celsius or degree Kelvin. So only the particular point or particular space or particular region. So how it being distributed, on which direction, it is not mentioned. So as a sum, what is the scalar quantity of that field? For temperature, current temperatures, every location has associated with number with units temperature, degree Celsius or degree Kelvin. So colors are representing surface temperature. On the contour lines, they are showing the constant temperatures. So quantitatively only we are mentioning the temperature. So fields are three-dimensional. Electromagnetic fields are three-dimensional. Vector fields. So vector fields, so not only giving the magnitudes but also the direction. Here the velocity vector. So here it is the velocity, that is meter per second, is mentioned quantitatively as well as with the direction too. So vector has both magnitude and direction in space. The magnitude of the vector is magnitude vector. It determinant of that vector, and also unit vector. Unit vector is the vector. So unit vector of any vector A is nothing but the concerned vector divided by the determinant of that vector, or the magnitude of that vector. For vector fields, the fluid flow, so it is also a vector quantity mentioning the direction. Gravitational field, it is also towards the earth, mentioning the direction. It is also a vector quantity. Magnetic field, so from north pole to south pole it is oriented. So here also the time is the direction is to be mentioned. In that reason it is also a vector field. The earth magnetic field behaves as if there were a bar magnet in it. So having north and south poles, earth is also a magnet. So unit vector is nothing but the vector whose mathematical quantity is 1. That's why it is unit vector. The vector components. So for any two vectors A and B, the dot product is A dot B and the cross product is A cross B. Here the result. So based on the result of dot product is a scalar. So the dot product is also called as scalar product. But the cross product of any two vector is given the vector quantity. That's why cross product is also known as vector product. Dot products A dot B is AB cos theta or BA cos theta. AX, BX, AY, BY, AZ and BZ. They are also the 3-dimensional magnitudes of the vector in X, Y and Z directions. So for any two vector to be perpendicular, the dot product is 0. For any two vectors, they are parallel. To be parallel, the dot product of that vector is 1. So A cross B cross product is giving AB sin theta into the unit vector. So A cross B. So how to determine the vector product of any two vectors A and B? So it is calculated by using a 3 by 3 matrix. In first row we have the 3 unit vectors AX, AY and AZ, the unit vectors on X, Y and Z directions. The second row, the 3 coordinates of vector A in X, Y and Z direction, that is AX, AY and AZ. The third row is about the 3 coordinates of the second vector, P vector, Bx, By and Bz. So the result of the determinant of A cross B. Properties of cross product A cross B is not equal to B cross A. A cross B is equal to minus of B cross A. So it is not associative. The vector product is not associative, but it is distributive. Scalar triple product A dot B cross E is B dot C cross A, and also it is equal to C dot A cross B. So it is applicable in associative. Vector triple product A cross B cross A is B into A dot C minus C into A dot B. So here the vector representations, we are using the 3 type of coordinate system: rectangular, cylindrical and spherical system. So for rectangular, so we can say as example sheets. So the sheet is having rectangle is example for rectangular coordinate system. The wires and the cables are of cylindrical coordinate system. So for analyzing wires and cables, we are using cylindrical coordinate system. Then spheres are being analyzed by the spherical coordinate systems. So what is a coordinate system? Capturing the information of a particular point in the space by different methods is called coordinate system. So three types are rectangular, spherical and cylindrical coordinate system. In rectangular coordinate systems, the parameters are x, y and z in the direction of x, y and z. All the three axes are mutually perpendicular to each other. That means x is perpendicular to both y and z. Y is perpendicular to both x and z. Z is perpendicular to both x and y. The spherical coordinates parameters are r, theta and phi. So in rectangular coordinates we have all coordinates are of length or distance vectors x, y and z. But in spherical, so only we have r only a distant vectors. The others two, phi and theta are angular measurement, angular vectors. In cylindrical coordinate system, so we have z, r and phi. The two are distant vectors. The phi is an angular vectors. So in this way we are classifying rectangular, spherical and cylindrical coordinate system. X, y, z for Cartesian, r, theta, phi for spherical, r, theta and z. Rectangle, how to represent a point in rectangular system. So the three axes are having the limit from 0 to infinity. So in which at any point we can represent using the rectangular coordinate system. So for any point P, so its coordinates are x1, y1 and z1. In cylindrical, so we have the limitations. The r distance is from 0 to infinity. Phi is varying from 0 to 360 and z is varying from minus infinity to plus infinity. So it is on the z direction. So going upward and downward from minus infinity to plus infinity. Spherical systems we have r, phi and theta. R is varying from 0 to infinity. Phi is varying from 0 to 360 as well as in the cylindrical coordinates. Theta is varying from 0 to 180 degree. So these are all some simplified relationship between any two coordinates. The first one is rho is equal to root of x square plus y square. So here rho is the cylindrical coordinate. So how can we relate the cylindrical coordinate rho with the rectangular coordinate x and y? Rho is equal to root of x square plus y square and x is equal to rho cos phi. Phi is equal to phi is a cylindrical coordinate. It is equal to tan inverse of y by x. Then y is equal to rho sin phi. For both the cases, the z is same. Z is same for the two. So using which we can convert the cylindrical into rectangular or the rectangular into cylindrical. Similarly, the relation between cylindrical and Cartesian. Cartesian is nothing but rectangular. Ux, Uy and Uz. So these are all the unit vector. Unit vectors in x, y, z, that is in rectangular, and u phi and uz, they are all the unit vectors in cylindrical. That's the relation between the unit vectors of cylindrical and rectangular coordinate system. So writing in matrix form, ux, uy, uz, the unit vectors in rectangular system. So how it is related with the u rho, u phi and uz, the unit vectors of cylindrical. Then the relation between spherical and Cartesian systems. So here the r is the spherical quantity. It is related with the rectangular quantities x, y, z. R equal to root of x square plus y square plus z square. And theta is tan inverse of rho by z. Rho by z or tan inverse of rho is nothing but cylindrical quantity, that is equal to root of x square plus y square. So theta is equal to tan inverse of root of x square plus y square by z. Then angle phi. So as previous, like in cylindrical quantities, so we have the same. The phi is equal to tan inverse of y by x. So in this manner, we can give the relations between x with the spherical quantities, y of Cartesian to the cylindrical and z of Cartesian to spherical. So x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, z equal to r cos theta. So using which we can solve any type of problems. So find the angle between two given vectors, a equal to vx plus 3z and b is equal to 5vx plus 2uy minus 6z. So we have to find the angle. The formula is tan inverse of y by x. So using which we can find the angle. Here the third problem, express the following vector in Cartesian coordinate and find b at -3, 4. So the given vector is a spherical vector in terms of r, theta and phi. So you have to convert it into a Cartesian coordinate system. So we have to write b in terms of dx, dy and dz at the point of -3, 4, 0. The area integrals, it is given by two directions, two delta distances, dx and dy. Example, so here the area covered by the red color. So integration is, it is nothing but dx and dy. So in dx it is 3 to 7, in dy it is 2 to 6. Area integrals. So area is, so integral of, so two variables x and y. So it is a double integral. So x is varying from 3 to 7, integral of 3 to 7, and y is varying from 2 to 6, integral of 2 to 6, dy dx, giving 16. So 3 to 7, the distance is 4, and 2 to 6, it is also 4. 4 into 4, 16. Z is constant. So it is no variation in z direction. In this course, area on surface methods will be on similar types of surfaces. R is constant, or phi is constant, or so any one is constant in area integral or double integral. So surface integral, we have two differentials, multiplication of two differentials dx and dy. The other is constant. So its direction is on the, so the third one. So here the result is the area is on the z direction. So for line integrals we have any length element. So area we have two vectors, the multiplication of two vectors. In volume vectors we have the product of two length quantities. Next, gradient. So gradient is nothing but the change, the differential change in the quantity is considered as gradient. So for any change, so in normal differentiation we have the change with by the letter d, dx, dy and dz. Here we have in 3 dimensions we have grade. So gradient of phi, it is nothing but, so dou phi by dou x, dou phi by dou y, dou phi by dou z. So having 3 coordinates x, y, z. So we have the change of phi in all the 3 directions. dou phi by dou x, dou phi by dou y, and dou phi by dou z. That is delta phi. So with delta, so what is delta? It's a differential operator. Dou by dou x, dou by dou y, or dou by and dou by dou z. So the physical meaning of gradient is the local variation of phi along dr. So in the direction of dr, how it is varying. Particularly grade phi is perpendicular to the line phi. Then divergence. So divergence is nothing but for any vector, divergence of any vector is nothing but the product of differential operator and that particular vector. So del dot A is the divergence of A. Del dot A. Divergence of any vector is 0 because it's a local conservation loss. If the mass of fluid outcoming from a domain is equal to the mass of entry, so being both equal, divergence, there is no divergence. So divergence of V is 0. V is the fluid velocity. So Laplacian definitions. Scale Laplacian. Del phi is equal to del square phi. It's a divergence of gradient phi. That is the second order differential. That is equal to dou square phi by dou x square, dou square y phi by dou y square plus dou square phi by dou z square. So gradient, divergence, curl, and Laplacian. Gradient is a vector. Divergence is a scalar because it is the resultant of the dot product. So curl is the resultant of any two vectors, so it is a vector quantity. So Laplacian is a scalar. Gradient giving a scalar field, divergence a vector field, curl giving a vector field, Laplacian giving a scalar field. The representation del phi is for gradient, del dot V is for divergence, del plus V for curl, and Laplacian is del square phi. So Gauss divergence theorem, A in equal A in and A out. So del dot A means the divergence of A, del dot rho U is the divergence of rho U, the net rate of mass flow from unit volume, that is equal to del dot rho U equal to divergence of rho U. Surface integral of the velocity vector U gives the net volumetric flow across the surface. So U, the velocity vector U ds is equal to U dot n ds, U dot n ds. So normal component, normal vector. So in this manner we can form the Stokes theorem and the Gauss divergence theorem. So here, so we can relate the line integral into a surface integral in Stokes theorem. But in Gauss divergence theorem, we can relate a surface vector with a volume vector. So integral of A dr, it is line integral. It is equal to a surface integral del cross A ds. So using which we can convert a surface integral into a line integral or a line integral into a surface integral. In Gauss divergence theorem involving surface integral and volume integral. So surface integral AD is equal to volume integral del dot A d sigma or volumetric, using which we can convert the volume into surface integral or surface integral into volume integral. We have already seen it is a cross product of the del operator and the concerned vectors. Stokes theorem. Okay, that's all about the unit 1, the fundamentals on the vector coordinate system. The second unit is about electrostatics. It is a branch of electromagnetics, deals with the effects of electric charges at rest. So it is giving the Coulomb's law. So Coulomb's law is giving the force between any two charges. Force between any two charges. So force between any two charges. Electrical phenomena caused by a friction are part of our everyday life and can be understood in terms of electrical charge. The effects of electric charge can be observed in the attractive or repulsion of various objects when charged. So whenever a thing is charged, so it can attract or repel. It can attract some other charges or being repelled by some other charges. So positive charge. If the two charges are positive, they are like charges. They are repelling each other. One is positive and another one is negatively. They are being attracted towards each other. Electron, the coulombic value of one electron is 1.6 into 10 power minus 9 coulomb. At the macroscopic level, we can assume that charge is a continuous one. So charges: point charge, line charge, surface charge and volume charge. So point charge Q, line charge rho L, that is coulomb per meter, charge per unit length. Surface charge density is rho S in coulomb per meter square. Volume charge density is coulomb per meter cube in 3 dimensions. So here we have some constants, permittivity constants. Epsilon naught, that is permittivity of free space. It is mathematically 8.85 into 10 power minus 12 farad per meters. Relative permittivity epsilon r. So normally for free space or vacuum, epsilon r is 1. So we can write observed permittivity epsilon is epsilon naught into epsilon r. Coulomb's law. So Coulomb's law, the statement of Coulomb's law is, for any two charges, the force between the two charges, it may be attractive or repulsive, is equal to the constant K into Q1 and Q2, the product of the two charges Q1 and Q2, divided by the distance between the two vectors R12, square of the distance between the two charges R12 square. So simply, the force between any two charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between the two charges. So the constant value K is 9 into 10 power 9 Newton meter square per coulomb square. So yes, there are number of charges involved in a closed surface. So we have to consider all the forces on one particular charge due to all the other charges. So summing all the forces, we can find the total force on one charge due to other surrounding charges. So in this manner, we can find the sum of forces particularly on one charge, one point charge. The force between two charges, the K is 1 by 4 pi epsilon naught. Then electric field energy. Electric field energy is nothing but force on unit charge. So any force but on 1 coulomb charge. The force on any 1 coulomb charge is considered as electric field energy. So if F is in Newton, the unit for electric field energy is Newton per coulomb. Newton per coulomb or volt per meter. So electric field or electric field intensity. Electric field due to a point charge. So EQ is K into Q by R square. The other one, the second charge is having the magnitude of 1 because it is force on unit charge. Electric field due to a collection of point charges. So connecting all the electric fields due to all charges on one particular unit charge. So summing all other we can find. So using the same principle we can find electric field at any point due to charge, the other charge. So it may be a line charge, surface charge. So for any kind we can find the total electric field. Some problems in determining the electric field due to line, circular and other charges. Then Gauss law determining the electric flux. So electric field lines, the summation of electric field lines is considered as electric flux. The flux passing through a surface. So that flux is equal to the total charge within the surface, within the closed surface. So that is Gauss law. So flux phi is equal to the integral of E dV. The total flux passing out any closed surface is equal to the charge enclosed by that surface. This is Gauss law. So Gauss law is applied on so many electrostatical problems. For any type of spatial, whether it is linear, cylindrical or volumetrical, or any type you can find the various electrostatic parameters using Gauss law. Then potential. The potential at any point is nothing but work done to move a unit positive charge from infinity to that particular point is considered as the potential. If we consider two potential points, so there is a potential difference between the 2 points. So difference of potential on these 2 points is considered as potential difference. So normally the charge will be flowing from high potential point to low potential point. Then the relation between potential and electric field intensity. Potential is equal to integral of EdL. So potential in volts, E is in Newton per coulomb, E into distance, the distance between the distance from the reference. So till V is E into V. So some problems in electrostatics parameters. Third unit is about the magnetism. So like Coulomb's law, here we have the Dr.S.Rajasekaran law in finding the magnetic flux density. Magnetic flux density dB is equal to mu naught by 4 pi I dx cross R by R cube, where mu naught is the permeability of the medium, 4 pi constant, I current, dx a small element, dx, R is the distance. So dB is mu naught I by 4 pi dx cross R by R cube, where integral of dl equal to mu naught I. It's a fundamental law for calculating magnetic field. So like Coulomb's law. So Coulomb's law, Gauss law for high symmetry. So like the electric field finding using Coulomb's law, here we are using Dr.S.Rajasekaran law for magnetic field calculations. For any type of conductors, linear, circular, we can find the magnetic field using Dr.S.Rajasekaran law. So here we are considering the moving point charges, that is current. Current is a moving point charge. The source for magnetic field is current. So using that Dr.S.Rajasekaran law, we can find any kind of magnetic fields for any type of conductors, whether it is linear, circular or cylindrical. Next, electromagnetic force. Electromagnetic force means the force constituted by both electric as well as magnetic field. It's a combination of electric as well as magnetic force. The total force F is equal to Q into E plus U cross V, where Q is, F is the force, electric force, Q is the charge. Charge means charge at rest, into E, electric field intensity, plus U is the velocity of charge. So magnetic field is created by the moving charge. So moving charge is having velocity u cross v. V is the magnetic field intensity. So it is known as Lorentz equation. So Lorentz equation gives the force due to electric as well as magnetic field. And magnetic forces and torques. So here the movement. So we have mechanical torques. So torque is torque. Equation for torque. So torque is R into F. R is the radial distance and F is the force. So we can derive the torque. The third one is electric and magnetic fields in materials. That is in electric field in capacitors, magnetic field in inductors. Here we have the Laplace and Poisson's equations. So using the electrostatic parameters, we have Laplace and Poisson's equation. Electric field lines, so capacitance and capacitors. That is materials, electrostatic materials. So V naught and V1, the two potentials on the plate and the plates. The distance between the plates, the capacitor plate is L. The field is electric field. The charge movement, charging of capacitor. Dielectrics. So dielectrics, there are no free charges but bound charges. Bound charges, they are polarized, negative and plus. So they constitute dipole. So boundary value problems for electrostatics. So like capacitors in electrostatics, here we have inductors. So inductors. Of Li square is the total energy saved in the magnetic material. Similarly, half CV square is the energy saved in electrostatic material. So electric and magnetic field in materials. The fourth unit, the last unit, electrodynamic fields and electromagnetic waves. So how to evaluate the electromagnetic waves? So propagation is by means of waves. And for evaluating these electromagnetic wave parameters, we are using the Maxwell's equation. So here we have so many kind of Maxwell's equations using which we can calculate so many the wave parameters. Magnetic induction, changes due to charge and the charging elements. So many laws. So using these laws, Ampere's law, Gauss law, and Ohm's law. So we have found the equation, Maxwell's equation. So the propagation of electromagnetic wave is perpendicular to both electric field and magnetic field. The propagation, if red is electric field and blue is magnetic field, then the propagation direction is perpendicular to both electric as well as magnetic field. So for using the three laws, we can form Maxwell's equations for solving any kind of electromagnetic waves. So we have separate equations for both electric as well as magnetic field, and the combination of electric as well as magnetic fields, using which we can solve any type of wave parameters. We can mathematically calculate any type of parameters for conducting materials, for dielectric, for any type of medium. We have different type of wave parameters using which we can mathematically evaluate any type of electromagnetic wave. Then point vector, so it is giving the energy energy propagated, when electromagnetic is propagated, what will be the energy propagated? Using this pointing theorem, we can calculate electromagnetic energy.